Hello there. Welcome to a special final edition of Team Wall Insiders, where a group of 4 senior computer engineering students bring you the latest tea on what is inside your walls. Here they shall be discussing their latest
award-winning
creation called Project Waldo. To start us off is Mr. Komara.
Hi, this is Team Wall Insiders, and this is Project Waldo. This is our final video submission for our senior design project. Hi, my name is Maurice Kamara. I am a computer engineering undergraduate at Cal State Long Beach. My role was to design the stud finder and base station modules, as well as program the server and position tracking system.
My name is Anthony Lee. I am a computer engineering undergrad at Cal State Long Beach, and my role for this project is to program and design the client application and also process data for the heat map generation.
Hello, my name is Oscar Serrano. I'm a computer engineering undergrad student at Cal State Long Beach, and my role for this project was to design the base station laser system, its stud finder enclosure, as well as any assembly of any necessary electronics for this project.
Hi, my name is Hayden Little, and I am a computer engineering undergraduate student here at California State University Long Beach. My role for this project was writing the firmware for our stud finder module and any of the IoT communications between the module and our database.
Project Waldo is a small handheld device that allows a user to scan a wall and then aggregates the data from a stud finder sensor to construct a heat map of the hidden studs behind the wall. The user can optionally visualize the stud data with a laser projection system mounted on the base station.
So our project's purpose is to allow individuals and users to view the entire wall scanned all at once. This resolves the problem of having to rescan a wall to find the studs, or making just ugly marks on the current walls and potentially making holes where you don't want them. This allows individuals working in construction or home renovation to just have data saved for a specific wall.
Technical details for the stud finder module. The stud finder module uses an Espressif ESP32 to capture data from a stud finder PCB and send it to the database server.
In the last couple of weeks, we tried implementing our own PCB that will have its own stud finder sensors and power system. Unfortunately, we ran into many issues with the design and the chip while troubleshooting, so we just ultimately decided to stick with our prototype module and use a commercially bought sensor.
The current stud finder PCB is from a Franklin ProSense M150 stud finder, where the outputs of the indicator LEDs are probed and inputted into the ESP32. Only the 3 central outputs are inputted into the ESP32, where they are compiled into a string and then averaged to output a single value, a 1 when there is a stud and a 0 when there is nothing detected. The ESP32 also connects to an NTP server, or Network Time Protocol server, where the time is captured based on the Universal Time Constant, or UTC for short. The time is adjusted to the Pacific Standard Time. Communication between the ESP32 and the server uses the MQTT messaging protocol. MQTT stands for Message Queuing Telemetry Transport, which is a lightweight publish-subscribe based messaging protocol. The stud finder module power on will have the ESP32 connect to the network, connect to the MQTT server, connect to the NTP server, then begin publishing a string with the stud indication and a timestamp every 0.5 seconds.
Our stud finder module has an external button to power on and an ergonomic handle to be able to firmly scan the wall. For our PCB design, which includes our ESP32, some status LEDs, and the wiring for the stud finder, we use KiCad to create the PCB and JLC PCB for printing.
Aside from the indicator lights on the stud finder PCB are 3 separate indicator LEDs. Green is for network connection, blue is for server connection, and red is for any failed connection. In the event of a failed connection, the ESP32 will restart its connection to the network, allowing for a refresh of any potential connection failures.
This is the technical details of the base station. The base station is the device that is positioned facing a wall and then placed a few feet away, which is in charge of taking a picture of the wall, tracking the position of the stud finder module, and turning on and positioning the laser for visualization. It uses a Google Coral dev board as the main computer inside. The device is powered by a 12-volt charger, which then uses regulators to step down the voltage to create power sources for the Google Coral board, laser, and servo. A camera is placed in front of the device that is connected through USB to the Coral board, which is running a program that tracks Aruko markers on the Stud Finder module. The program also connects to our MQTT server and sends the position tracking data over the network. It also receives any commands to take a picture or to turn on and position the laser. The software is programmed in C++ using CMake as a build system and uses libraries such as OpenCV and libmosquito. Technical details for the server. We are hosting a server which is in charge of running an MQTT broker, coordinating data between the Stud Finder module and the position tracking system, and hosting an API for our database. The coordinator program reads position data from the base station and Stud Finder data from the handheld module through MQTT. It then combines that data into one data point and stores it in a SQLite 3 database. In addition, a web server is hosted that allows other applications to send queries to manipulate and pull data off of the database. The software is written in C++ using the CMake build system, using the micro HTTPD library to host the web server, libSQLite 3 to interact with the database, and libmosquito to send and receive data from the MQTT network.
This is the technical details of the client application. The client application is a user-friendly interface for the user to create and store wall scanning sessions that they can select to generate a visual heat map of their desired wall and enable the laser projection system on the base station. The application is programmed in Python using tkinter, a standard GUI library. Communications to the server database is done through the HTTP communication protocol using the requests library, a HTTP library built for the Python programming language. Communication for the laser generation system and overlay image capture is done through the simple MQTT commands, 2 topics for the base station and server. MQTT communication is done through the Eclipse Paho MQTT Python client library. Requests from the client application are done by sending SQL queries, which is then sent as packets to where data is then retrieved from the database and is then received and processed by the client application for updating the GUI with up-to-date information on things such as recorded wall sessions or as data for heat map generation and stud identification. Incoming data from the database is processed utilizing the NumPy and Pandas library. Heat map generation utilizes the heat mapping function provided by Seaborn, a data visualization library based on Matplotlib. Award-winning
While working on this project, there were a lot of obstacles we had to overcome. For example, after working on the server for a while, it became really slow to access, and we had to upgrade the server in order to continue debugging and verifying our data quickly. In addition, we had to learn a lot of new software and libraries such as MQTT, OpenCV, SQLite 3, Seaborn, and FreeCAD. We chose to use the Google Coral Dev Board in our project, and that had a huge lack in documentation and a lot of outdated software in the default operating system.
Adding on to the obstacles that we overcame was probably determining the components to fit our requirements for a decent price. We also figured out the tolerance for 3D printing so it would be strong enough but it wouldn't take too long to print. Also determining the best method for precision tracking in order to track our stud finder module while we scan the wall.
So continuing on with our long list of obstacles that we had to overcome for this project, one obstacle that we had to also overcome was determining the best representation for the stud data when generating the heat map, and also identifying possible stud locations for laser projection. Finally, a major obstacle that us as college students had to overcome when taking this class was balancing our time between our personal and academic life.
Okay, so adding on to our list of obstacles that we overcame, due to poor connection of our phone hotspots where we were testing, we resorted to connecting to the school's Wi-Fi just because it was more reliable and available to connect to anywhere on campus, from where we were testing to the classroom where we were doing our demonstrations. Continuing with that, we had to make sure that we were sending the correct payload packages or messages via MQTT to our server database for use for the client application and position tracking. For our 4 main goals of our project and whether they're met. So for our first goal was to being able to scan the studs and track the stud finder module's position. That one is good. For our second goal was being able to record and send data on the located studs from both the stud finder module and the position tracking to the server and store it within our database. That one is good. For our third goal was generating a visual heat map of the data acquired from the database to the user. Third goal is good. For our fourth and final goal was being able to identify possible stud locations and project it onto the wall via a laser. That one is also good. So that means that all 4 of our main goals were completed for this project.